Everybody, and welcome to our next video. Today's topic is going to be on some more limit stuff and asymptotes. We're going to kind of finish up our last tiny little bit of information that we can gather when we look at limits and how that translates to a function's graph. So if you recall, there are times that a function may increase or decrease without bound as we approach a particular value of x. This is referred to as an infinite limit because the result of the limit as x approaches c of f of x equals plus or minus infinity. So visually, if you guys recall, as we get closer to a particular value of x, we are approaching some kind of, that does not look good, sorry. We are approaching that vertical asymptote or that particular value of c, and as we do so, we are either increasing without bound, or not sure what's going on here right now, sorry, or decreasing without bound. Oftentimes, the function will go to different directions on either side. It's not always the case. Some functions, both sides will go to positive or both will go to negative infinity. But the idea is, as we approach that particular value of x, the value of the function is increasing or decreasing without bound. The values are getting really big in the positive or negative direction. Whenever this limit exists, it is an automatic guarantee by definition that a vertical asymptote must exist on the graph of the function. And it's really important for us to just be able to determine those pieces of information, whether we're looking at the graph or looking at an equation of the function. One really easy way to determine where those infinite limits and vertical asymptotes occur is to think of the domain of the function and where those non-removable discontinuities will exist. So we've kind of already looked at this in a more informal way in the first few sections. This is really just kind of going back and highlighting this and making it more of a formal piece here. So the idea is whenever we evaluate that limit as x approaches a finite value and our result is positive or negative infinity, it is now an automatic rule. For sure, you guys should know that there is a vertical asymptote that exists on that graph. So we're going to start here with a really complicated looking one. There's lots of pieces here. So this function is going to have a good bit of issues going on, but we're going to break it down into pieces and use that to help us identify what's going on. So our function f of x is equal to the product of two rational functions. So the first fraction is x squared minus 5x minus 1 over x minus 7. And then the second piece, x squared plus 3x plus 2 all over 2 minus the square root of x plus 3. And we want to know at what values of x does the graph of f have a vertical asymptote. So really the first thing we need to do is kind of explore the domain of this function. So again, domain is basically we're going to identify all the values of x that we have to restrict the function at. So what can we not substitute into this function? So since this function is a product of these two rational functions, we're just going to explore restricted values within each one and see what the final result is going to end up being. So for the first one, there may be a 4 missing in your guided notes packet. If you're using our guided notes that go along with the videos, please make sure that it says minus 14 at the end. So knowing that, remember with rational functions, anytime that we have these polynomials involved, factoring everything is a pretty important piece of the puzzle here. So when we first look at this guy, x squared minus 5x minus 14, that numerator is factorable. This could be rewritten as x minus 7, x plus 2, which is really helpful or important to us to identify when we're looking for vertical asymptotes. Because again, all restrictions on x in your domain will show up graphically somehow, either as a vertical asymptote or as a hole. So in this case, the restricted value from the denominator is that x cannot equal positive 7. However, because that factor shows up in the numerator and denominator, that restriction could be removed and we rewrite the result in another way, which would allow us to have a hole on the graph, not a vertical asymptote. So I'm going to go ahead and mark that down right now so that we don't forget it. Now, for the second fraction, this numerator could be factored to be written as x plus 2, x plus 1. But then that denominator That guy doesn't actually factor because it's a radical expression, not a polynomial expression. So we're going to have to simply set this guy equal to 0, and then we're going to solve. So remember, to solve radical equations, we want the radical by itself, and then we can get rid of it completely using exponents. So I'm going to move the radical to the right side here. So we get 2 equals square root of x plus 3, and then we'll square both sides. Again, it's always the reciprocal power of whatever the radical is. So square root is 1/2, so the inverse of that is squared. So I get 4 equals x plus 3, and then whatever the end result is after the radical is gone, just solve it like a normal equation. So in this case, subtract 3 from both sides, so we get x equals 1. So if I were to substitute 1 into this entire function, these other 3 parts are all going to be non-zero values, but this denominator would turn into 0. So we have a restricted value at 1. However, there are no factors of x minus 1. So if this is a value that makes this guy equal to 0, if there was a factor anywhere in the numerator that said x minus 1, then plugging 1 into the top and bottom would both result in a 0 over 0, the indeterminate, which we could try and manipulate and get rid of, and could eventually turn into a whole. So because that's not the case here, we know that this guy is going to be a vertical asymptote on this graph. Now, to fully explore the domain, just to take this another step further, because this radical expression is a part of this function, it wouldn't matter where it shows up in the function, but if radicals, including variables inside, are used, we have to consider the fact that with every radical of an even power, or even root in this case, that inside has to remain positive or 0. So we have to explore what values of x break that. So in this case, x plus 3 always has to be non-negative. So in other words, x always has to be greater than or equal to 3. Negative 3. So if we were to take a look at the real number line, or the x-axis, from negative infinity to infinity, we would be first restricting this to all values greater than or equal to negative 3. So all of these guys are gone. But then at positive 1, that would be the first other restriction. So we can't use that value, but again, we know that that would be some vertical asymptote on the graph. And then after that, we know 7, there is a restriction on it, but that would be a hole somewhere on the graph. And then after that, all those other values of x would be able to be used and have no issues. So out of all the restrictions that are going on here, 1 is the only place where a vertical asymptote occurs. So what that tells me is the limit as x approaches 1 from the left, or the limit as x approaches 1 from the right, each of those, and actually I shouldn't use an equal sign here, so we're just going to think about them individually. Those two limits, as we approach from the left or from the right, we don't know exactly, without going into more detail, which one it's going to, but we know that each of those is either heading towards positive infinity or negative infinity by definition. So again, this is what we talked about a few minutes ago. So every time that you can identify a vertical asymptote, you know for sure that the limit as we approach that value of x from each side is either going to go up or down forever without bound. Now we're just going to use a little bit of logic to take information about limits to kind of piece together what exactly we know is going on the graph of the function. So we're told the function f is continuous at all values of x except for x equals 3. So again, that idea of continuity, we've explored different ways that functions could end up being discontinuous. So one of them is we could have a vertical asymptote. So the function could go up forever or down forever. Again, it could be heading in the same direction on both sides. We don't always know all that given information, but we know for sure that on each side you're going to some kind of infinity. Or option 2, it could be a hole in the graph. So as we approach that value, the limit does exist for the function, but the value of the function could be defined. So it could be up top here, or there may not be an extra point whatsoever. But in either case, either the second or that third condition of continuity fails. That says that the limit as x approaches c is equal to the value of the function of f at x equals c. So there we have holes, and then that third issue is where we have that jump discontinuity. So it could be a hole on one side, defined point on the other, but it's just simply a break in the graph where you have to jump from one portion to the next. But again, these do not naturally exist. We can't just write one equation and have a jump discontinuity exist like this unless you have some really weird functions that we're not going to dive into right now. But 99% of the time, if this is what the graph looks like, it has to be defined as a piecewise function. So those are the three major types of discontinuities that we want to be on the lookout for. So if we're told that it's continuous at all values of x except for 3, one of these things should be occurring at 3. It's the second piece of information that will allow us to figure out exactly what's going on. So the second piece says the limit as x approaches 3 of f of x equals infinity. So if we have that second piece of information, out of these three options, we're able to rule out it can't be a hole, because if it was a hole, then the limit would be a finite value, not infinity. And it can't be option 3, because the limit at x equals 3 would not exist. So we wouldn't even be able to say an infinity, because we're approaching two different values from either side of 3. So in this case, because they're telling us the overall limit is infinity, we can put together that with the fact that it's discontinuous at x equals 3 and the limit is equal to positive infinity, the graph would have to look something like that on either side of that vertical asymptote. So that's what the big takeaway here is. This function must have a vertical asymptote at x equals 3. That's why it's discontinuous, but why we can describe the limit value as being infinity. Okay, now for this next one, the function f is continuous at all values of x except x equals -2. So again, we're kind of exploring this same idea. Which one of these three do we know about? And then, but for this one, it says the limit as x approaches -2 from the left side of f of x is negative infinity, but from the right side of -2, it's positive infinity. So if you think about the discontinuities, again, it can't be the second or the third option. It's got to be the first one, but now this graph would look slightly different. So at x equals -2, from the left side, y values are approaching negative infinity forever. And then from the right side, we're approaching positive infinity forever. Now, I'm just drawing this arbitrarily with a horizontal asymptote on the x-axis. We wouldn't know that to be true, but what we do know to be true is what the end behavior is doing as x approaches -2 from the left and right sides. So once again, we have to have a vertical asymptote at x equals -2. We can prove that definitively based on the information that they gave to us. So our first few examples, we're taking a look at when we evaluate a limit as x approaches a finite number and our result is some kind of infinity. But now we're going to take a look at when we flip that around. So we use something called limits at infinity. So when we take the limit of a function as x increases or decreases without bounds, so we're not approaching a number now. Instead, x is approaching positive or negative infinity. We'd have to indicate which one we're actually using. But when we do that, we call it a limit at infinity. So basically, we want to know what are the y values doing as we continue to plug in bigger and bigger x values. So if this process produces a finite number L, then we can say definitively that the function has a horizontal asymptote represented by the equation y equals L. So if you think about that, if you are approaching, the y values are approaching a finite number as x gets bigger and bigger, that means on the graph, as we continue to move to the right or left forever, the y values would have to be leveling out. And eventually, the difference between that finite value we're approaching and the actual value of the function are so microscopic or infinitesimally small that they're almost the difference is almost indescribable. We can't really distinguish a difference anymore between those two. So if a limit at infinity yields any other result after all options for evaluating limits have been exhausted, then we know the function cannot have a horizontal asymptote. So this is kind of like what we just talked about before, but in the reverse order. So what we were just talking about is if I know a function has a vertical asymptote, then we know the limit has to be approaching infinity. But now we're saying if x approaches infinity and the limit exists and is a number, then we can prove that a horizontal asymptote must exist. So you guys have done this in Algebra 2, pre-calc. This isn't anything totally brand new. The concept has existed for a while, and you've seen it in different ways and in different classes, but we're just going to kind of extend it a little bit further for the purposes of this course and introduce a few more comparisons that you may not have seen just yet. So when we are looking at or exploring if a function has a horizontal asymptote, 90% of the time we're going to be looking at rational functions because they are comparison of growth rates. So how does the top function compare to the bottom function? And if they compare in a particular way, then that yields a particular result for their final ratio. When it's not a rational function, some functions still have horizontal asymptotes, but there are other ways that we can manipulate them or interpret them that can actually produce fractions, and kind of explains why those asymptotes exist in the first place. So one thing to keep in mind is how quickly or slowly functions grow. So out of all the functions that we talk about, or you guys have seen in the past and we'll see again in this course, we can kind of put them on a scale of the slow ones compared to the fast ones. So out of all the functions that you guys have seen, logarithmic functions grow very slowly. If you remember, they look like this guy, okay, and they've got a vertical asymptote because they're the inverse of exponential functions. And because of that relationship with exponentials, these graphs grow vertically very slowly. They jump horizontally very quickly, but vertically they grow very slowly. And it's not a coincidence that their inverse or counterpart exponential functions are actually the fastest growing function that we will work with. In between those two are all of our other guys. Polynomials and radical functions are kind of in the middle here. So how those grow are really dependent upon what power is representing that particular function. So cubics will grow faster than quadratics. Linear functions will grow faster than square root functions because square roots are really the half power of x. So the middle guys, it's really all about what exponent are we working with. Now, the only one that's not listed on here are trig functions, and that's because trig functions are very special depending on which trig function that we are working with, and we're going to talk about them when we get down here to this guy. So there's something special there. So when it's really important that when we are evaluating these functions to identify horizontal asymptotes, that you guys keep in mind how quickly or slowly different functions are growing compared to one another. Because the rule is that when I have a slow function over a fast function, so that means the denominator is going to get big faster or really quickly, and the top is not, it may be approaching a constant value, so it's never going to change, or it's just changing or increasing at a much slower rate than the bottom. When that happens, the gap or the distance between the value of the numerator and denominator gets much bigger very quickly, and because of that, we always will end up with the result of a horizontal asymptote at y equals 0. When the numerator and denominator grow at the same rate, then it's always a matter of how their leading coefficient. So whatever function or term determines the growth rate of the numerator and denominator, we compare their coefficients to create the horizontal asymptote. And I'll show you what that looks like here in a minute. And then the last guy, the third option, is when we flip the first one. When I have a fast-growing function over a slow-growing function, well, that's the exact opposite of this first guy. And as you guys start to kind of piece together these limits things, you're going to realize that the reciprocal of 0 in many cases is actually represented as infinity. So 0 represents the infinitesimally small, infinity represents the infinitesimally large values. So let's dive in and take a look at some of these. So for our first function, we've got f of x equals e to the x over e to the x plus 2. So when we're trying to make these comparisons between which function top and bottom grows slow or faster if they're growing at the same about the same rate, um, you have to keep in mind that some of the functions top or bottom might have extra terms that as x grows very large, the value of those extra terms become irrelevant when comparing to the size of another term in the expression. So for example, in the denominator here, we have e to the x plus 2. So as x grows larger and larger, e to the x, the parent exponential function, is just going to continue to increase without bounds. So adding 2 onto that is not really going to play all that big of a factor when we compare it to just e to the x by itself. So for example, if I plug 1,000 in for x, e to the 1,000 power is a really big number. So what we have is a really big number on top divided by that same really big number, just with an extra 2 added onto it. So what this really turns into essentially is these guys are the only important parts when trying to think about the value of this fraction as x grows very large. So when we are making these comparisons, we really want to isolate what is the most important term in the numerator and the denominator, and then we make these comparisons. All of those extra terms become irrelevant, so we just kind of ignore them when we evaluate this ratio. So in this case, because these are both e to the x, or exponentials, when comparing two exponentials, you have to compare their bases. So the bigger the base, the faster the growth. Smaller the base, the slower the growth. Or in this case, they are the same base. That's the exact same thing. So in this case, this is a same over same situation. So the ratio of their coefficients, or in this case, 1 over 1, would yield our horizontal asymptote. And again, if you think about the size of top and bottom, they're always going to be right about the same value. The bottom is always just going to be 2 more than the top. But in the grand scheme of things, with really, really big values, 1,000,002 is not that much bigger than 1,000,000. So the ratio is going to be about 1. All right, so for the next one, again, we want to search for the most important term in top and bottom. So in the numerator, the largest degree term in this polynomial is an x cubed. So all these other guys, when x is very large, won't be growing as fast as the first guy, so they don't contribute as much, so they're not as important. And then in the denominator, the largest degree there is from the term negative 2x cubed. So this is another same over same situation. They're both polynomials, so we're in the same category. And then we are comparing their degree, so they're both x cubes. So same degree, same growth rate there, but the denominator has a coefficient of negative 2, so that one's going to grow slightly faster than the top. So that's why we take their ratio of their coefficients. So in the grand scheme of things, the value of this fraction as x grows very large is going to be about negative 1/2. So one thing to keep in mind as we are doing this, when we're checking these asymptotes, we're really answering the question, as x approaches negative infinity, what's f of x approaching? And as x approaches positive infinity, what is f of x approaching? Now, for a polynomial rational function like this guy, we never have to wonder. Both of those limits, if there is a horizontal asymptote, are going to be the same thing. So no polynomial rational function can have two different horizontal asymptotes. If there is a horizontal asymptote, it's always the same thing. So we know that this is the only horizontal asymptote for this guy. But I want to jump back to this first one real quick and just make sure that we can answer that same question. So what I had done the first time around was as e to the x, or excuse me, as x grows to positive infinity, this is that asymptote. So I'm going to write that notation down here. So as x approaches positive infinity of f of x, we know that ratio is approaching a value of 1, and that's what yields the horizontal asymptote. But that limit as x approaches negative infinity is a little bit trickier. So as x approaches negative infinity of this quantity, I want us to think about the value of this guy. So even though infinities, those symbols are not numbers, we could still kind of write them in the place of x, and that just makes us think of what is really happening. So I'm going to do that. I'm going to rewrite this expression as e to the negative infinity over e to the negative infinity plus 2. And now there are two ways to try and figure out what this value is. So the first one is interpreting this graphically. E to the negative infinity is like saying, I'm going to go to the graph of e to the x and evaluate its limit as x approaches negative infinity. So remember, one of the properties of limits is if I take the limit of a quotient, I can evaluate the limits of numerator and denominator separately and then take their ratio. So that's why I can think of what this graph of just the top e to the x is approaching as x goes to negative infinity. Well, on this graph, as we go to negative infinity, this graph is approaching 0. So I know that this numerator actually has a value of 0. And when this same expression shows up in the denominator, that guy also has a value of 0 and then plus 2 for that constant value. So overall, this limit is equal to 0. Now, another way of interpreting that e to the negative infinity is with a little bit of exponent properties. E to the negative infinity, remember a negative exponent means to reciprocate the base, so this is really equivalent to 1 over e to infinity. And now to evaluate that guy, we can think about on the graph of e to the x as x goes to infinity, whereas this exponent grows larger and larger and larger, e to the infinity is also approaching infinity. And from our past experience, 1 or any non-zero number divided by an infinity means that the bottom is going to get really, really big while the top stays small, which is the same thing as saying that it's approaching 0. So there's a couple different ways to interpret this e to the negative infinity part, but no matter how we do it, we're going to get the same result, 0. So this is a unique example of a function that has more than one horizontal asymptote. It's a very common thing with exponential rational functions to have these extra asymptotes because one side we're plugging in negative exponents, the other we're plugging in positive exponents, and they behave kind of in an inverse, or have an inverse relationship with those. So this function actually has another horizontal asymptote at y equals 0 as well. So it's a special function that has two of them. So that doesn't mean both sides use both of these asymptotes. If we were graphing it, we would draw them the whole way across, but that doesn't mean the graph is going to interact with both asymptotes on both sides of the graph. The left side would be approaching 0, the right side would be approaching 1, and we can take a look at this real quick to see what that graph would actually look like. So if I type e to the x over e to the x plus 2, you guys can see to the left, we are approaching 0, and then on the right, we are approaching 1. So it's a special kind of graph with those two asymptotes. All right, so now let's dive down to this guy. So h of x equals sine of x over x plus 4. So again, we want to consider both of these limits. Limit as x approaches negative infinity of f of x, and limit as x approaches positive infinity of f of x. So for the negative infinity part, if I plug really big negative values into the numerator, this sine of x function, it's a special one. So if you remember, I'm going to give us some room here. The sine function has the special property, and same with cosine, where its output values are restricted between -1 and +1. So we're always bouncing back and forth between negative and +1 on this sine graph, which means no matter what x value I'm working with, I am always going to be somewhere in between negative and +1. So as x grows very large, that means even though we're not approaching a specific value, the size of it is very slow. We consider that a slow growing or a non-growing function because the bottom is going to be either getting bigger or smaller, but whatever it's doing, the top is kind of locked in, or it's almost considered a constant function. So this bottom, or excuse me, the top we're going to consider very slow. And then the bottom, because sine is always bouncing between -1 and 1, it's always going to be slower than any other function that we compare it to, because as long as the other thing's value is growing past a value of 1 or -1, then it's going to be bigger in size. So x plus 4 would be a fast function. So in this case, slow over fast means that we are approaching a value of y equals 0. So we have at least one horizontal asymptote. And then on the other side, positive infinity, well, neither of these functions change how they're growing as we go to positive infinity. So these guys would still both be approaching 0 as well. So that is our one horizontal asymptote there. All right, now for our next one, k of x equals 3x squared minus 4x plus 7 over 5x minus 2. So we've got another polynomial over polynomial. So this one's a little bit easier. We're just comparing the exponent size. So most important term of the numerator would be 3x squared, largest degree. And for the denominator would be 5x. So this would be a case where we have a faster growing quadratic function over a slower growing linear function. So because of that, this guy would have no horizontal asymptotes because again, the limit as x approaches negative infinity or positive infinity, both of these are, actually I should separate them. So as we go to the left side, so as x approaches negative infinity, well, if we think about it graphically, this top guy is a quadratic. So we know on the left side of the quadratic, we are going to positive infinity. So we're getting really big positive numbers. And then the bottom guy, 5x minus 2, is a positive slope linear function. So on the left side, we're getting really big negative numbers. So the ratio of them, the overall value of this guy, the top is getting bigger faster than the bottom is. So overall, we are going to infinity. But in this case, we would be going, because it's a ratio of positive and negative values as we're doing that, this would result in negative infinity. So that tells us the movement on the graph. So the end behavior of this function, as x goes to the left, the y values are going down forever. And then if we consider the other side as x goes to positive infinity, well, doing the same kind of stuff, right side of the top would be going to positive infinity, right side of the linear is also going to positive infinity. So the right side of this graph is going to positive infinity. So if you remember back to pre-calc or algebra 2, when we have a quadratic over a linear, this is one of those graphs that have a slant asymptote of some kind. And because there's a vertical asymptote in there, the graph is, it's either pinched in between these two sections, so it looks kind of like that, and these ends are where the limits that we just evaluated come from, or it could be the case where it's on the outside edges, so it looks like this guy in the orange. But even still, we would still see those two limits show up that we found. So this guy has a slant asymptote, but no horizontal asymptote. We know that for sure because of the growth rate of the two functions. All right, next up, we've got p of x equals 2 to the x minus 4 over e to the 3x plus 2. So if we try to compare these, again, we have exponential functions on top and bottom. So we only need the relevant pieces of the top and bottom. So that would be 2 to the x compared to e to the 3x. So because they're both exponential, now it comes down to their bases. So for e to a non-x power, whenever e is raised to some other power, you have to be able to use some exponent properties to break it apart to truly evaluate what the base of this function is. So e to the 3x, undoing some exponent properties, I can write that as e cubed to the x power. If you remember, when I have a power raised to a power, we multiply those exponents. So this is just the undoing of that process. So if I regroup them as e cubed to the x, whatever the value of e to the third is really the base value of this denominator term. So if I were to evaluate e to the third power, I would get e to the third roughly 20, a little bit more than 20. So obviously, e to the cubed is going to be bigger than the numerator's base, which is 2. So that would mean that this would turn into a slow over a fast grower. So we know that we have 0 mixed in here as x goes to infinity. So again, those relationships that we talked about in the first one, particularly with exponentials, when we just compare growth rates right off the bat, we're typically doing it as we're approaching positive infinity. So I know I'm going to 0 that way. But when we go to evaluate limits as x goes to negative infinity, then everything kind of has the reverse effect because of those negative exponents. So let's think about this now with these negative exponents in mind. So if I were to do a similar thing as what I did up top here, this would result in 2 to the negative infinity minus 4 over e to 3 times negative infinity is still just going to be a very large negative number. So negative infinity plus 2. So whenever we have these exponentials raised to these negative infinite powers, these guys are always going to result in 0 because when I rewrite this piece here, it really turns into 1 over 2 to the infinity, and 1 over that exponential power like that, that is always going to result in 0. So this turns into 0 minus 4, and then on bottom, I have 1 over e to the infinity again. So that guy also turns into 0. So we end up with 0 plus 2. So this yields, again, another secondary horizontal asymptote, in this case, whoops, of negative 4 divided by 2, or negative 2. So this is another example of one of these functions where we have two horizontal asymptotes. So one at y equals negative 2, and then one at y equals 0. All right, and then our last example here, 4x minus 5. So most important term there would be 4x over 3x squared. So this would be another case where we have small over, slow over fast. So a slow growing function over a fast growing function always results in a horizontal asymptote of y equals 0. So again, for these three functions on the right, these are all polynomials over polynomials, which is why we don't have to consider the difference in limits to the left and to the right, because again, those are guaranteed to only have at a maximum one horizontal asymptote. Now we're going to take a look at another topic that's closely related to limits and continuity. It's actually an application of the idea of continuity. So there's some important theorems that depend on being able to show a function is continuous on a certain interval. And one of them is called the Intermediate Value Theorem. So it is defined as if f is a continuous function on the closed interval a to b, and d is some number between f of a and f of b, where f of a does not equal f of b, so that means they don't have the same endpoint, same y values, then the intermediate value theorem guarantees that there's at least one number c in the interval between a and b, such that f of c equals d. So I'm going to try and map out all of that information graphically for us. So I'm just going to pick arbitrary values or points. So we have an interval of x values from a to b, and each one of those has an endpoint. So whether one's bigger than the other, I'm not going to, there's no like guidelines on that. Again, they're just arbitrary values. So when x is a, y is f of a. When x is b, y is f of b. So really the only two conditions here are that the function has to be continuous. So remember, that goes back to our definition of continuity across an interval. So at every point between a and b, the function is continuous, which means the function's value is defined. So f of c exists for every value of x between a and b. So there's no holes, no asymptotes, no jumps. And then the limit as x approaches c for every value exists. And then those two values are the same thing. So we're saying that the function must be continuous along those, or along that interval, which means somehow, some way, these two endpoints must be connected by a smooth continuous curve. Now, how that's accomplished, it can go up and down. We could go up past it, do whatever. We could do all kinds of crazy stuff. But if it really is continuous, then I must have connected these 2 points with a continuous function somehow. So if that's true, then what the intermediate value theorem says is for any y value between the y values at the two endpoints, so we just pick an arbitrary spot in there, d, there's got to be at least one time inside of this interval, at least one place where the function has an x value that produces that specific y. Now, this is the example I drew. There are 3 places where that happens. It doesn't always have to be that way, but we know for sure that there's at least one. And it's all based on this idea that the function must be continuous. So because of that, it rules out all of the what ifs. Well, what if there's a hole at that particular value? What if there's a jump discontinuity and we jump up over that y value of d and we go past it? By guaranteeing the function is continuous, we're able to rule out all of those crazy possibilities, and it only leaves us with a smooth continuous curve. So because of that, we know for sure that every y value between the two endpoints of the interval must be used at least once. So for example, suppose that there's some continuous function f, and we know that f of 0 equals 2. So that would be our endpoint, our left endpoint, and then f of 4 equals 6. So if we know that, or we can guarantee that at least one x value uses every possible y between 2 and 6, as long as, again, we know that it's a continuous function. So again, the easiest way to connect these would just be a straight line. So every y value is used at exactly one x value. But it doesn't guarantee that it looks like that. Again, it could go, it could do all kinds of crazy stuff in between. We can go up and down, make all kinds of twists and turns. So if someone asked you, is it possible to find a value of c between 0 and 4 such that f of c equals 5, to answer that, we would just have to make sure, does this desired y value fall between the y values of the endpoints? So 5 is between 2 and 6. So yes, because it's a continuous function, we must have used that y value at least one time. So let's take a look at a few examples where this intermediate value theorem can be applied. So for the first one, it says the following table gives some function values for the continuous function g of x. We want to know, is it true that there exists some c in the interval 0 to 2 such that f of c equals 5? So when we are trying to apply the intermediate value theorem, we're basically just checking two conditions. So first off, is f continuous? So sometimes it will tell us directly in the problem. So for this case, now I'm sorry, g of x instead of f of x in this case. But essentially just, is the function continuous? Because if it's not, then it doesn't matter the rest of the conditions or any of the numbers that they give us. We can't do anything if the function is not continuous. That's the most important condition or part of this. So in this case, we know it's continuous. So that means wherever these endpoints are, they must be connected without any holes, asymptotes, or jumps. So the second part is your d value, or in this case 5, somewhere between the endpoints of this function? So it could be the case that f of 0 is the smaller of the two endpoints, or it could be the other way around. We don't know necessarily if the function decreases or increases as a whole over the course of this interval. But as long as one of these two are true, that the y value is somewhere in between. I'm sorry, we need to get rid of these equals. As long as it's somewhere in between those, then we can guarantee that there is at least one place in the interval where it uses a y value of 5. So typically we will be given an equation like these other two examples, and we'll actually have to substitute some values in. And when we substitute those values in, then we can see how the desired y value compares. But in this case, they just gave us a table of y values that we're going to look at. So we know it's continuous. So now we need to evaluate the ends of the interval, which is 0 to 2. So our first value, g of 0, is equal to 7. And then g of 2 is equal to 3. So again, sometimes it's helpful to see this graphically. So at x equals 0, y is 7. At x equals 2, y is 3. So again, a continuous curve to connect those means at some point, because 5, yes, it is in between these two. In this case, it's this one that passes. Our first y value is actually the bigger of the two. But because our desired y value exists between the two y values at our endpoints, we know for sure somewhere, the only way I can connect these two dots is with a continuous curve, is to at some point pass through the y value of 5. It could happen more than once, but we definitely know that it happens at least one time. So in this case, yes, the intermediate value theorem applies. So that means there must be at least one place where f of c or excuse me, this should say g of c is equal to 5. Now, had I given you an equation instead of a table of values, then we could actually use the equation, set it equal to 5, and then we could actually do more work. We could actually go and find the values of x where y is equal to that desired value. But in this case, that's not what we need to do. All right, so let's try this next one. A little trickier because this is a piecewise function. Remember, those are always a little more difficult. But this one says, let k be the function defined by k of x equals the piecewise defined function x plus 2 when x is less than or equal to 1, and x plus 4 when x is greater than 1. We want to know, is it true that there must exist some x between 0 and 2 for which k of x equals 4? Okay, so again, let's check our conditions. Intermediate value theorem. First condition is continuity. So again, the interval we're concerned on is from 0 to 2. So the individual pieces are polynomials. They're linear functions, which means we don't have to worry about discontinuities as a whole somewhere else on their function. But the only spot that we have to be specifically concerned about then is their transition. So positive 1 is a value within this interval. So if it's discontinuous at 1, then this fails. So we need to check for continuity at x equals 1. So to do that, we are going to use the definition for continuity. So if you remember, first condition would be, does f of 1 exist? So if I were to, or excuse me, in this case, k of 1. So if I were to substitute 1 into this piecewise defined function, the top function uses 1 in the interval, so I can plug that in and evaluate it at 3. So the first condition of continuity passes. Second condition is, does the limit as x approaches 1 of k of x exist? So we need to evaluate that. Remember, for piecewise functions, when we're evaluating at the transition, that is where we check the one-sided limits. So we're going to check 1 from the left and from the right. Hopefully they will match up. If not, then we know the function is discontinuous. So from the left, again, it's a polynomial, so we can use direct substitution here, but that means we would use the top function. So plugging 1 in, we know is 3 because that was the value of the function. And then for the right-sided limit, now we're greater than 1, so we're using the bottom function. That would be 5. So obviously looking at that, those one-sided limits do not equal the same value. So because of that, the overall limit as x approaches 1 does not exist. This would be the example of a piecewise function with a break in the graph. So because of that, the continuity condition fails. So if the function cannot be guaranteed to be continuous on the interval, then there's no way to guarantee that that particular value of y is used. So in this case, or actually let's graph this a little bit more accurately. So we know it splits at x equals 1. Up until that point, we were using the x plus 2 function, which stops at a value of 3. So that guy would look like this. And then we jump up to the x plus 4 function, which we know at x equals 1 would start at 5. So this, in fact, the function itself actually does jump over the desired y value of 4. This function would not ever produce any y value anywhere between 3 and 5 because of the two pieces that are used being linear functions and the fact that we're jumping up over that interval between 3 and 5. So the intermediate value theorem fails here because that continuity condition fails. So this is an example of where this intermediate value theorem would not be able to help us learn any information. But if we take a look at one more example here, so we're going to consider the function s of x equals 2x squared plus 4x. And we want to know, is it true there must be some value c between 0 and 1 for which s of c equals 3. So, okay, intermediate value theorem. So first condition, continuity. So we need to know, is this guy continuous on the interval from 0 to 1? Well, the answer to this is an automatic yes, because this is a well-behaved function. This is a quadratic. We know all polynomial functions are continuous on their entire interval, so we don't have to worry about checking anything. We know this guy to be continuous. So the second piece is a matter of our endpoints. So we need to figure out what does S of 0 equal and what does S of 1 equal. So S of 0, plugging 0 in for x is just going to yield 0. But plugging 1 in there is going to give us 2 plus 4 or 6. So now it's just a matter of comparing. And in this case, yes, S of 0 is less than 3, which is less than S of 1, or another way of saying that, 3 is in between 0 and 6. So that second condition passes. So because of that, yes, we know for sure there is some value of x between 0 and 1 for which our function is equal to 3. Now, if we wanted to, because we know it exists, we could take the equation and set it equal to that value and then ask you to solve for that exact value of x where that y value occurs. So in this case, this is a quadratic. If I wanted you to do this, I know the directions don't say it, but it's a little fun extra add-on, and we get to review the quadratic formula. I would solve by getting everything to one side. You could try to factor this with the AC method. You need numbers that multiply to make -6, add to make +4. There are none, which means this guy is not factorable. So instead, we would use the quadratic formula. So x would equal the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So my discriminant in here, we get 16 plus, because of the double negatives, 24, or the square root of 40. So I need to evaluate -4 plus or minus the square root of 40 all over 4. Let's see, 40 is the same thing as 2 square roots of 10 over 4, or you divide out a 2 from everything. Actually, let's just go ahead and jump to a calculator to evaluate this guy. So I'm going to take -4 plus the square root of 40, and then divide that answer by 4. So we get 0.58. So that value occurs within our interval, but let's check the other way. Now, if you think about it, though, the other version of this is -4 minus the square root of 40, which would produce a negative value. So in this case, it's not worth our time to find that other guy because our interval is only from 0 to +1. So we know that the value of c that we were actually looking for is 0.581. That is the value of x that produces that desired y value. So one of the biggest applications of the intermediate value theorem is the fact that we can use it to actually prove where x-intercepts must exist for a function. So another way that this could work is if I were to produce an interval or give you an interval of x values where one produces a positive y value and another produces a negative y value, well, that proves, as long as the function is continuous, that there must be at least one x-intercept or value where the y value is equal to 0 somewhere in between those two endpoints or within that interval. So that's just another application of this intermediate value theorem.